Here is an important theorem called the Rolle's theorem, but before I get into Rolle's theorem, one has to know the difference between continuity and differentiability. So, if a function f of x is differentiable, in other words, a derivative exists on some interval, then the function is continuous on that interval. However, the converse is not true. So, if a function f of x is continuous, that is, there are no jumps, breaks, infinite discontinuities, then the function is then the function may or may not be differentiable on that interval. So, for example, suppose we have a parabola. We know that parabola is differentiable. And since it is differentiable, just by looking at it, we can say it is continuous. But let's take an absolute value function. Now that function is certainly continuous, but it is not differentiable for all x. Why is that? Because there is a sharp turn. In a similar manner, we could take a function of this sort It certainly looks continuous. There are no breaks, but it is not differentiable. For all x. The reason being, you have what we call a cusp. So just because a function is continuous doesn't mean it is differentiable for all x. But if we know that a function is differentiable, then it is guaranteed that the function is continuous for all x. So that said, what does Rolle's theorem state? Rolle's theorem states that suppose f of x is a continuous function on the interval, closed interval a comma b, f of x is differentiable on the open interval a comma b. We say the open interval a comma b because we can't find derivatives at endpoints. So in this case, the endpoints are a and b, so we cannot have a derivative at the endpoints, hence we say that f of x is differentiable on the open interval a comma b. And let f of x be, or f of a be equal to f of b, then there exists a number c that is in the open interval a comma b, so that means in, such that f prime of c equals 0. Now I will demonstrate 3 different cases here. So even though it says mean value theorem, I'm just going to go ahead and draw it here. So case 1, let's say you have a continuous function between a and b that is constant. So f of a clearly is equal to f of b. Then no matter what point I pick, let's say I have point C there, then the derivative f prime of c would be equal to 0 because this is a constant function. So if you take the derivative of a constant, you will get 0. Case 2. Suppose I have a function of this sort. I have a and b. So the derivative over here is increasing. Or we can say on this side, the derivative is positive. On that side, the derivative is negative. And why is that? Because derivative is simply the slope. So on the left-hand side, we have a positive slope. Right-hand side, we have a negative slope. So the derivative has to be positive on the left-hand side, and it has to be negative on the right-hand side. So clearly, there is a point C right in the middle, where the derivative is 0. Right at that point, the tangent line is horizontal, which would imply the derivative at that point has to be 0. So Rolle's theorem checks out. And another case would be a function of this sort, f of a, f of b. They are the same. The same applies over here. and the function is continuous, the function is differentiable, clearly it's the parabola, and there exists a point C right here where the derivative will be 0. On this side, the left-hand side, the derivative is negative because it is decreasing. On that side, the derivative is positive because the slope is positive. And right here, the tangent line at that point is horizontal. So there, the derivative f prime of c will be 0. So that satisfies Rolle's theorem. Rolle's theorem states that if I have f of b is equal to f of a, then there has to be a point C between a and b so that f prime of c would equal 0. That's exactly what I've wrote. And that C has to be between A and B. An extension of Rolle's theorem, or a theorem based on the Rolle's theorem, is the mean value theorem. The mean value theorem states if f of x is continuous on a comma b, and f of x is differentiable on the open interval a comma b, then there exists a number c that has to be in the interval a comma b such that f prime of c is equal to f of b minus f of a divided by b minus a. So there has to be a point that satisfies that condition. And that is what we call the mean value theorem. And the key here is C has to lie between A and B. Now, clearly, if you go back to Rolle's theorem, you can easily verify with the mean value theorem. So, if f of b is equal to f of a, it's one of the conditions in Rolle's theorem. Then f prime of c is equal to f of a minus f of a, because f of b is equal to f of a divided by b minus a, 0 over b minus a. So f prime of c is 0. So for some arbitrary number that is between a and b, f prime of c will be equal to 0. That verifies Rolle's theorem in an indirect way. So we want to verify that the function that is given here satisfies the three hypotheses of Rolle's theorem on the given interval, then find all the numbers c that satisfy the conclusion of Rolle's theorem. Now, first thing, we want to know if it is continuous. If you graph this, f of x is a parabola. So this is continuous. And could we take the derivative? F prime of x would be 4x minus 4. This is a linear function. F of minus 1 is 2 times minus 1 squared, minus 4 times minus 1, plus 5. So that would be 2 plus 4 plus 5, I get 11. F of 3 is 2 times 3 squared minus 4 times 3 plus 5, which is 18 minus 12 plus 5, I get 11. This implies f of minus 1 equals f of 3. So that is A and that is B. So we have a condition in Rolle's theorem that is satisfied. So we have a continuous function, we have its derivative, and we have the condition where f of minus 1 is equal to f of 3. Now we have to find a function c so that the derivative is equal to 0. So all we have to do is set f prime of x equals 0 and solve for x to get the number c. So this would imply 4x minus 4 is equal to 0. 4x would be equal to 4, which would imply x is equal to 1, and that 1 lies in the interval -1, 3. So that would mean the Rolle's theorem is satisfied. Good. Now I think it's better to have a calculator so you can verify if in fact a function is continuous. Let me go ahead and sketch the function. So if you sketch the function 2x squared, minus 4x plus 5, I'm going to set the window -1 to 3, and I'm going to graph, and that is the curve that I get. And clearly between those 2 points the function is continuous, and you can see at 1 the derivative has to be 0 because it turns at that point. So Rolle's theorem is satisfied. Now here is another function, x plus 1 over x on the interval 1/2, 2. So let's see if it is continuous. Change the window, graph, and that's what it looks like. And you say, oh well, maybe Rolle's theorem may not be satisfied in this problem because it doesn't look like there is a dip. So let's see what happens. Clearly it is continuous. Now, the next thing is to find the derivative, which is 1 minus 1 over x squared. Then we have to find f of 1/2, which is 1/2 plus 1 over 1/2. It's 1/2 plus 2. You get 5 over 2. And f of 2 would be 2 plus 1 over 2, which is still 5 over 2. So f of 1/2 is equal to f of 2. This would imply there has to be a c that is in 1/2, 2 such that f prime of c equals 0. How do we find that c? So set f prime of x equal to 0 and solve for c, which would mean 1 minus 1 over x squared equals 0. So 1 would be equal to 1 over x squared equals 1, which means x is equal to plus or minus 1. We can ignore -1 because it's outside the interval that I have, which is 1/2 to 2. So the number c is simply 1. But is the derivative 0 though? By looking at the picture, it doesn't look like it. The reason is because we did not set the window properly. So let me just set it between 0 and maybe 3. And now you could see at 1 there is a turn. So we actually have a point C at 1. So it sort of goes like this. So that would be C equals 1. And that would be 2. And I should probably start at 1/2. And those two values are one and the same. So Rolle's theorem is verified. So here is an example where we have to verify our mean value theorem. So what does the mean value theorem state? The mean value theorem states that if f of x is continuous and if it is differential, there has to be a number c which would satisfy f of b minus f of a divided by b minus a. So that should equal to f prime of c. So let's see if f of x is continuous. Obviously it is going to be because it is a parabola. Set the window 0 to 1. So that's what I get. So it is continuous. Maybe I could even adjust it furthermore and get a better picture. Looks continuous to me. 0.5. Okay, so we have a graph that is continuous. So a, f of x, is continuous. Now, f prime of x is 6x minus 3. Now, f of a is 0, b is 1, is 2 times 0 squared minus 3 times 0 plus 1, I get 1. F of b is equal to f of 1, which is 2 times 1 squared minus 3 times 1 plus 1. 2 minus 3 plus 1, I get 0. So let's see if we have a number. So the question is there a number C that is in 0, 1 satisfying f prime of C equals f of B minus f of A divided by B minus A. So the mean value theorem states that there is a C. Let's see if there is a C. So f prime of C would simply be 6c minus 3, because we know the derivative is 6x minus 3. So 6c minus 3 would equal to f of B minus f of A divided by B minus A. F of B is 0, f of A is 1, B is 1, A is 0, which would give me negative 1. So 6c minus 3 equals negative 1, 6c equals negative 1 plus 3, 6c is equal to 2, which means c is 2 over 6, and c is 1 over 3. C equals 1 over 3 certainly lies between 0 and 1. So mean value theorem holds true. Sometimes, depending on the function, it may not be true. So here we have another function that is between 1 and 3. So is f of x continuous? Yes, it absolutely is. We can verify that. If you graph it, set the window between 1 and 3. The y values have to be between 0 and 1. Let's graph it, and it is continuous. So between 1 and 3, the function is continuous. Let's find f prime of x. F prime of x is minus 1 over x squared. Then we have to find f of b and f of a. F of a is f of 1. That is simply equal to 1 over 1. We get 1. F of b, so that would be equal to f of 3. It's 1 over 3. So according to MVT is mean value theorem, there must be a C that satisfies f prime of C equals f of B minus f of A divided by B minus A. Let's see if that exists. So f prime of C is minus 1 over C squared. F of B is 1 over 3. F of A is 1. B is 3. A is 1. So we have negative 1 over C equals negative 2 over 3 divided by 2. We can get rid of the negatives. So 1 over C squared would equal 2 over 3 over 2, which would imply 2 equals 2 over 3 c squared. The 2's would go away, which would imply c squared equals 3. So c has to be plus or minus square root of 3. We can ignore negative square root of 3 because it is outside the domain that we have, which is between 1 and 3. So clearly, c equals square root of 3 lies on the interval 1, 3. So this would imply that MVT, or mean value theorem, holds true. So if we know that a function is differentiable and continuous, then there has to be a c that lies between a and b so that f prime of c is 0. Oh, excuse me, f prime of c is equal to f of b minus f of a divided by b minus a.